Hello guys, welcome here to another video. We'll be continuing with the series of circle geometry, and today I just want to take you through a more theoretically no numbers oriented and more into the proofs and matching proportionality within the circle geometry. This will be in June 2022 question paper 2 for mathematics grade 12. And we'll be looking specifically at question number 10.2. Let's correct that. So that will be 10.2. And because of the intensity of the question, will be, for this part of the video, we'll focus at 10.2.1 and 10.2.2. And we'll carry over to another part of the video for the last two questions. All right, let's commence. The statement reads as follows. There is a diagram which I have drawn here, where O is the center of the circle, and we've got points A, B, C, and D which are sitting at the circumference. There is a line EC. They're telling us that line is the tangent to that circle. And then there is a diameter dB. So dB is a diameter, and we can see that it's a line starting from here, passes through the center and back to the circumference. They are also mentioning that diameter dB produced meets at EC at E. So they're saying this diameter continues up to that point. F is a point on EC such that BF is perpendicular to EC. Alright, so there is F, and they're saying BF is perpendicular to EC. Then they are also telling us that there is a radius CO, and it's also produced in here such that it bisects AG so AD. So when they say bisect, it means it cuts or intersects such that it divides AD into two equal parts, which is AG and GD. All right, let's continue with question number 10.2.1, which is asking us to prove that FB is parallel to CG, and we must provide reasons. All right, so 10.2.1. CG. Okay, so that's the first question. So they are saying provide reasons, and now I've always iterated that we must always provide the reasons when it comes to circle geometry. This is always to make sure that whoever is looking at your script or is trying to understand whatever you wrote on the paper, they can at least understand your train of thoughts and whether you are indeed understanding what you're doing. So for FB parallel to CG, that side there is parallel. So we need to first identify those two lines, and we must now think of different ways to prove what, or how do we prove that two lines are parallel. So let's first note, where are these lines? FB is this guy here, FB, and there is CG. Okay, therefore we must prove that these lines are parallel. Okay, I'm gonna put it there because I am positive that we will prove that it is parallel. And once you have proven it, try to label that on your sketch so you don't forget it. Okay, when lines are parallel, you must always think of, okay, what do you benefit from parallel lines? What theories go along parallel lines? So the first one is that we'll have angles that are equal, but those angles are judged by whether we're talking of alternate angles or corresponding angles. So the first part of the solution is understanding that parallel lines give us alternate angles they also give us corresponding angles. I'll attach a video which explained or exactly sketchically what do we look for in corresponding angles. But in a nutshell, we are looking for alternate angles. We are looking at Z. So these angles in here, they are equal. So that's if these lines are parallel. For corresponding angles, I consider it as F. So we have lines like this. We have this line parallel to this one such that this angle now is equal to that, and we call that corresponding angles. The last one is, so I called it opposite angles or parallel lines are supplementary. So this is, I call it your U shape. So that's opposite interior angle. So you look for a U shape. In here, we've considered Z. Corresponding, we looked at F. So when we now speak of these opposite angles of formed by these parallel lines, supplementary, we consider a U shape. So for that, the reasoning becomes opposite angles of parallel lines are supplementary. When we talk of angles, we look at, so if we have a line like this, these opposite interior angles here, those are supplementary. So that's your U shape. So that's what you look for when you're trying to prove that indeed certain lines are parallel. So let's go and look at our sketch and think or use these theories to see what can assist us better. So the first thing I should say is that as I'm writing these on the board, make sure that if you are quick to forget, make your job easy. When they ask you to prove parallel lines, quickly jot down notes. Okay, for parallel lines, I have these three to consider. And how do they look like? You quickly sketch this so that you can always visualize what you are trying to prove. Okay, so to go back to this sketch, to prove that FB is parallel to CG, we have to go back here. So we can see that if these lines are parallel, we are already forming that U in here. There's already an F. So if you look at this shape here, this is an F. So we can try and prove that this indeed is equal to this. These ones should be supplementary, these should be equal, corresponding angles. And then we also see a nice Z there. So we have various options. We can prove that this angle is equal to this one, or this entire angle is supplementary to this one, or this angle here is indeed equal to this one. Any one that can make your job easy. But we can already see that for alternate angles, it's going to be hard because we need to first find what is that angle and this one, so we can prove that they are indeed equal. You have to scale. So for us to prove alternate, we need to do how many steps? Prove 2, find the angle of 2 there, of B2, find the angle of C2. So that is almost, I should say, two points to look at. If we look at this, the U shape, you see that we have to first find F2 and also have to find the value of GCB, so this angle in here. Okay, for corresponding angles, which is F, we can see that there's already an angle there, F1. We just need to make sure that we prove that GCF is indeed equal to F1. So we see that we need to go for one step to prove that one, and I always go for the easiest route. So we can see that here we can start by proving that there are corresponding angles, and from there we can then say therefore the two lines are parallel. So the first point is to find angle ECG. So ECG, so that's the angle ECG. What is that angle? Okay, to find that angle, we are already told that there is a radius in here. There's a radius. The goal is to prove that, because we already know that F1 is 90 degrees. And for corresponding angles, it won't always be this case, but fortunately here we know that there is F1 being 90 degrees, and therefore ECG must be 90 degrees in order for us to prove that they are corresponding angles. So we ask ourselves, what can make this angle 90 degrees? So you think, okay, there is a tangent there, and there is a radius. So they told us there's a radius OG. And think, what combines a radius and a tangent, especially if they intersect? What theorems surround that? The first one I can think of is that a radius intersecting a tangent will always intersect it at 90 degrees. There are other theorems that surround tangents and then radius, but the one that quickly connects a tangent and a radius is that those two, when they intersect, they form 90 degrees. So important things: the radius must intersect the tangent, and then there needs to be a tangent. What is a tangent? What is a radius? We can go deeper into that, but if you are interested on knowing more about tangents as well as radius, please comment on the comment section below. But for now, we already see that GC is perpendicular to EC. Okay, so ECG is equal to 90 degrees because this is an angle. So a radius OC is perpendicular to EC, and we call that a tan perpendicular to chord theorem. It's tan perpendicular to red theorem. Some people call it the tan red theorem. Some people call it just the radius intersecting EC. They explain the thought process. So you can go for this explanation that the radius OC intersecting the tangent will always intersecting the perpendicular. Other people can just say it's a tan red theorem, and we will know what is there. So we found that ECG is 90 degrees, but so therefore, because we know ECG is 90 degrees and F1 is equal to 90 degrees, this is given. So, or you can firstly state that. So F1, so angle F1 is equal to 90 degrees, and the reason here is that it's given. That angle is given to us. So therefore, these two are equal. F1 is equal to ECG, equal to 90 degrees. Now, since those two angles are equal, then FB is parallel to CG. Therefore, FB is indeed parallel to CG. The reason is that corresponding angle. Corresponding angles. So let me quickly explain. We're saying FB is parallel to CG. How did we prove that? We found these two angles and we found that they are indeed equal. Now, when you state that it is indeed parallel, you have to state that the angles you found, how are they related? We see that they are equal, but what theorem or what rule did you use to prove that they are indeed, or would you associate that to the two lines being parallel? So we know that we used the F rule, which is corresponding angles. All right, let's go to the next question, 10.2.1 B. Let's go to B. All right, 10.2.1b, we are asked to prove that triangle FCB is, this sign is for similar triangles, is similar to triangle CDB. All right, So let's first try to locate those two triangles in our sketch. The first one is FCB. So FCB. So this is the triangle we're looking at. And CDB, CDB. This is the triangle we're looking at. And we're asked to prove that those triangles are similar. So you can either, so I don't like using the word cram, but do understand that to prove that triangles are similar, you can either go the angles route, or you can mix angles with sides, or you can consider all sides, so proportionality. So angles that are similar, they are proportional. They are equal, and they are triangles that are similar, they are also proportional. So similar, you should understand, doesn't equate to being equal triangles. As you can see that this triangle is smaller than this one, but we can prove that they are similar. Similar being that there is proportionality between them. And sort of about that. In this case, if you go with the sides, so let's say you can choose to go with sides, proving with sides. So sides being proportionality. You look at sides, are these sides being are they proportional? And you can go with angles. Angles. The last one is to mix angles. So mix angles with sides. Side plus angle. All right. To prove that sides are proportional, you need to, when you look at your sketch, at least have a feel that, okay, maybe they have given numbers to the sides, like how long are these sides, what units are these? And we can already see here that we are only given angles, and these are the only sides that have been marked as being equal. So you can probably dig deeper to find that there are values you can associate with the sides, or you can link that this side maybe is proportional to this one, but it's going to be a very long route because there are no numbers in here. We can mix sides with angles. We have already seen that the sides are not numbered. By numbered, like I said, we're not told how long is one side. It can be 2 centimeters, or we can say 2 units. The other one can be 4 units. Then you can start looking at proportionality when you can see real numbers. Or sometimes they can be labeled into variables. So one side can be x, the other one can be 3x. So you can somehow link them in terms of numbers and then talk of that they are proportional. But in this case, we are not given such. So you can already see that if you mix sides with angles, it's still going to be a long route. Please do indicate that if you need a video where I can show you how do we sketch these, how do we link, when we say sides plus angles, where are we looking at exactly sketching? Then now the last one is angles. Angles, we have plenty of angles in here, and we can fight to prove them. Plus it is circle geometry, and circle geometry is purely about angles. Not only, but mostly angles. Okay. In angles, this is what I'm going to focus on. When we look at angles, if you have 2 triangles, this triangle and this one, then you have A, B, C, and you have D, E, F. Like we are seeing there, this triangle, if drawn to scale exactly like that, is never equal to this one, because you can see the sides are big. But to prove that they are similar, we just need to prove that 2 of the angles in there, they are equal. 2 of the angles in there are equal. Let's say, for instance, A is equal to D and C equals to F. So what you have proven there is that A is equal to this angle and C equals to this one. If those 2 can be linked to angles in there, definitely this one should be equal to that one. That's why you just need to prove two angles. You don't need to tell us about the last one, because angles in the triangle all need to add up to 180 degrees. So if two are being equal, then definitely the last ones should be the same. Okay, so we need to work around that. So in our sketch, can we try to use that train of thought to help us locate angles that are indeed equal from the two triangles? All right. Do you remember? We have just worked with this triangle in here. We must remember that FB, we've just proven it that it is parallel to this one. Okay. So the first bet is, how can I link angles in here, just two angles, to this triangle? Okay, so the first one is that we can already see that this is a triangle that is special. It's special because it touches the circumference on 3 points. That's the first thing. Through practice, you'll be able to sort of imagine all of these things, but as I always note in our previous videos, try to just open your mind when you look at circuit geometry, and even if it's from the start of the question, just pinpoint what things may help you in the future. They might not really contribute to most of the answers or even at all, but it's worth understanding or feeling or being dominant on the question at hand. So what I've just done here, I looked at the question and I'm like, what is special about these two triangles? The first one is that it touches that circumference on all 3 points. What that helps me with is that already I can know that if there is a tangent and then that tangent touches any of those points, we can start looking at tan chord theorem. But if this triangle ended somewhere here, so it was not fully like on the circumference, then I can't go about using tan chord. So I can already see that EC is a tangent to this circle, but it is touching the C point. So that's the first part. The second one, so we can look at, so triangle CDB. This is purely for your benefit. You can even put this on your script just to make sure that the marker understands how you're thinking. So CDB touches the circumference on C, D, and B. So this is all the points. So the second thing to note, so from that you can already see that that gives back to tan chord theorem and many others. Let's see, are we finished with that? So another one is, there's something special which they told us on the statement that DB is a line, is a chord that specifically passes through the center. So it's a diameter. And because, like I said, CDB is touching the circumference on all points, when a diameter closes that specific triangle, we can already see that we can have the angle at the center being twice the angle at circumference. It opens up many opportunities. So you can already see that we have a diameter in here, and we can start locating that. We can start already figuring out different angles. So I am excited, you should be. So there is DB there, which is a diameter. So these are just to note. Let's go to the last one. So this is FCB. FCB, what is special about that one? We have worked with FCB on the previous question, but we worked on F1. And F1 was 90 degrees, so we can start thinking or being excited on how to figure out other angles there. But one thing to also note is that FCB is involved in the parallel lines in here, so maybe that can give us the benefit in finding other angles in here. But now let's act. First thing, we're trying to prove two angles that they are the same in these two triangles. The first one, there's a diameter, and the diameter subtends like an angle that is at the circumference. So we can already know that from the theorems that we know of circuit geometry that a diameter subtending a certain angle, that angle has to be 90. Or what I like to do is flip that. Diameter is a 180 degrees line. Diameter is passing through the center and is subtending this. So the angle at center should always be twice the angle at circumference. And if this is 180 degrees, then that angle DCB should be equal to 90 degrees. So let's start. Therefore, DCB, the angle DCB should be equal to 90 degrees because it's angle subtended by diameter. What is that diameter? Is dB. Alright, that's the first angle. So what angle can we link these two on the other triangle, which is FCB? We see that FCB, we must find an angle that is 90 degrees. And we already are given an angle there that F1 is 90 degrees. And these are on a straight line. They told us that this is a tangent and the tangent is a straight line. So on a straight line, those two angles that are split there should always be equal to 180. So F2 plus F1 should be equal to 180 degrees angles of straight line. Don't write like me, write properly. So those are angles of a straight line. They sum up to 180. We already have F1. F1 is 90 degrees. So if we take F1 from 180, so 180 minus 90 degrees is definitely equals to 90 also. So angle F2 should be equal to 90 degrees. Alright, we have proven that there's one set of angles that are equal in there. We must prove the last one. Remember, we've just used this one now, that diameter. Let's look at the first one, where we have CDB touching the circumference on all points. We said that gives birth to Tanko theorem. It also gives birth to this rule that we used in here. Let's see how we can use the first point. Okay. C1. So there's a tangent, and then there is our triangle there. It's given. So if there's a triangle that touches the circumference of the circle on all the points, and there's a tangent which somehow intersects that triangle, then there must be a Tanko theorem in there. Look for that angle, find it, and tell us about it. Find it. That's the first step. So tan, that's the tan. Which chord is this? This is the chord. So we have that the angle subtended, the angle between the tangent and that chord is equal to the opposite angle of the triangle that is subtended by the same chord. That is the theorem. Okay, C1 is equal to D2. C1 is equal to D2. Reason, tan, what is the tangent? It's tangent EC, chord. What is that chord? Is CB, tan chord theorem. From the tan chord theorem, tangent, chord, CB, we gave birth to this rule that these two angles must be equal. We have proven two angles in these triangles that they are equal. So therefore, these two are similar triangles. All right, let's move on to the last question. All right, question number 10.22 is asking us to prove or to give reason why this angle might be equal to 90 degrees. First thing, find that angle. Where is G1? G has two angles, G1 and G2. So that is that angle. Okay? They are saying prove why it might be equal to 90 degrees. So when you are surveying this, what pointers do you see? You see that there's a line from center here that is somehow touching this one. Okay, but what we also see, which we have been told, is that this line intersects or bisects AD. When you say intersect, it means it touches. So a certain line intersecting another one means it touches that. When you further describe it as bisect, it means this is a special touching. It is dividing that. When it intersects that line, it divides it into two equal portions. So AG is equal to GD because this line OG bisects that one. Okay, what rule do we know? What theorem do we know about that? This has been flipped around. Normally, we say a line from center that is perpendicular to a chord will bisect the chord. But here we're given two lines that are equal, that have been bisected by a line from center. So the opposite should also be true, that if we see two lines that are equal, mainly because they were bisected by a line from center, then that line should form 90 degrees when it bisects that two. So the reason is that line OG from center, line OG from center, bisecting AD must be perpendicular to AD. That is the rule of thumb. And therefore, G1 is indeed equal to 90 degrees, and we are done. Please look out for the second part, which will focus on the last two questions of the question paper, specifically for this diagram.